Welcome back to CS Connect series. In this video, we will be discussing about digital logic gates. Logic gates are nothing but circuits. So this hardware related concepts take a base from mathematical concept which is propositional logic. I would suggest you to go to mathematical logic playlist and watch propositional logic video. Now we'll get into digital logic gates content. We have already learnt about binary data. So we know binary data is nothing but two element data, one is 0 and another one is 1. What is this binary logic? When you are going to apply logical operations to binary data, that will be binary logic. So let's take binary logic. What does it have? It contains binary variables and logical operations together. So that is combinedly called as binary logic. What are the binary variables? We usually represent them using capital letters or small letters. What are the logical operations? We can term and or not as of now. Whenever you use these binary variables along with the logical operations, the result will either be 0 or 1. That's why we are terming this as binary logic. It is not about the number of operands, it is about the number of elements that we are dealing with. I would like to remind you what's a truth table here. This is a table of all possible combinations of the variables, showing the relation between the values that the variables may take and the result of the operation. Every combination is listed in a separate row. If there is a combination of 1 and 0, that will be listed in a separate row. When it is 0 and 0, it will be represented in a separate row. So if you have idea about truth table, I think you will be able to understand these two statements. Now we are getting into the title of the video. Logic gates, otherwise called as logic circuits, otherwise called as switching circuits, and then it is otherwise called as digital circuits. Okay, what are these circuits or what are these gates? They are blocks of hardware that produce logic 0 or logic 1 output signal. So what are the different logic gates that we are going to discuss in this particular video? We'll start with buffer. This buffer will actually do no operation, but it is like a storage area, we can say. We have NOT operation, which is negation in propositional logic, and operation, which is conjunction, or operation, which is disjunction. Then we have another set of 4 gates: NAND, NOR, XOR and XNOR. All these 3 gates are actually basic logical operations. The gates in the right hand side actually depend upon these 3 gates: AND, OR and NOT. Now we will start with the buffer gate. So this is the representation of buffer gate. The representation is termed as graphic symbol. So whenever I want to represent 0, a red color will be used. Whenever I want to use 1, the green color will be used. So the appropriate values will be filled in the truth table when we see the operation. So what happens when X is supplied the value of 0? I said buffer will not do any operation, it will just act as a storage area. The output will also be X. So when I pass 0, I get 0 as the output. What happens when I pass 1? The output will also be 1. So this is 1 and 1. This is a very simple gate which is going to give you the same output that it receives in the input. So the algebraic function is given by f is equal to x. What is this? We are just doing no computation and retaining the value of x, that is f is equal to x. So whatever input is received, it is just given as output. This is buffer gate. Now we will move to the inverter gate, which is the NOT gate. In the graphic symbol, you could have found f is equal to not x. It means you are going to negate the value of x, which is going to do the negation operation in logic. So here the first value that we are going to supply to x will be 0. When I invert 0, what happens? In propositional logic, when we negate false, what will happen? It will turn to true. So here the value of f will be 1. So the first row value will be when x is 0, the output will be 1. We are just inverting the bits. That is why we call the gate as inverter gate. What about x is equal to 1? You have to invert the value of 1. What will you get? You will get 0. So when x is equal to 1, the inverter gate will give you 0. So what is the function of this particular inverter gate? It will invert the value of the input. When 0 is passed, it will give you 1. When 1 is passed, it will give you 0. The algebraic function is represented as f is equal to x dash. We can represent it as x bar. Both are actually right. So this is actually representing not x. Now we are moving to the AND gate. Here AND operation will involve two variables. When you want to perform AND operation, you at least need two variables. For the inverter gate, you need only one variable because you are going to just reverse the value. If it is 0, you are going to give 1. If it is 1, you are going to give 0. But for AND, OR and others, you at least need two variables as input. This is the graphic symbol of AND gate. So let's start with x is equal to 0 and we will have y is equal to 0. 0 and 0 will give you 0 only. So f is also 0. This is the first row. What about x is equal to 0, but now we will change y's value as 1. 0 and 1 will give you 0 again. This will be the next row. What about x is equal to 1 and y is equal to 0? This time we will have 0 again because 1 and 0 will also give you 0. What about x is equal to 1 and y is equal to 1? When both the inputs are 1, you will get 1 in the output as we see in the final row. So what is the AND operation doing? F is equal to 1 only if both x is equal to 1 and y is equal to 1. F is equal to 0 when both x and y are 0. Otherwise, either x is 0 or y is 0. The algebraic function is represented by x into y. So usually we represent multiplication by star in arithmetic, but here they use dot operation. You can represent it as x into y or just xy, both are same. Now we will get into the OR gate. This is the representation of OR gate. So first let's start with x is equal to 0 and y is equal to 0. 0 or 0. What it will do? It will give 0 only. That is the first row. Now x is equal to 0, but we will change the value of y as 1. 0 plus 1 will give you 1. So this is the next row. What about x is equal to 1 and y is equal to 0? So here 1 plus 0 or 1 or 0 will again give you 1 only. So this is the third row. What happens when x is equal to 1, y is equal to 1? 1 or 1 will give you 1 again. So this is the final row here. What does the OR gate do? F is equal to 0 only when both x is equal to 0 and y is equal to 0. Otherwise, when either one of them is going to have 1 or when both are going to have the value 1, the output will be 1. The algebraic function can be given by x plus y. This plus is not equal to arithmetic operation. This is logical OR. If you take arithmetic operation, 1 plus 1 will give you 1, 0. But logical operation is 1 or 1 will give you 1 only. So we have completed the basic three operations AND, OR and NOT. We saw a term called switching circuits initially. So we will just elaborately see what they are. Electronic digital circuits behave like a switch with the active elements such as transistor either conducting when the switch is closed or not conducting when the switch is open. So let's take the switches in series. So here they have given something like active elements such as transistor. This transistor is going to decide whether to conduct electricity or not. This is actually open position. When it is in open position, it will not conduct electricity. Say for example, the voltage source is given here. From here the electricity will be passing this way. If it is open, it will stop here. In case if it is closed, it will flow through this particular direction again. Again when this is open, it will stop here. If it is closed, it will again flow through this way and the lamp will be glowing. Why are they called switches in series? Because they are placed one after the other in the same row. This arrangement is actually depicting logical AND operation. Only when A is closed and B is closed. What do we say? Switch closed. We are saying it is going to conduct electricity only when they are closed. So at that time you can take A is equal to 1 and B is equal to 1. When both are closed, the electricity will be conducting. That's why 1 into 1 or 1 and 1 will give you 1. Imagine A is going to have 0. The electricity will stop here. So when A is equal to 0 and B is equal to 1, even if this particular circuit is closed, when A is open, the electricity will not be conducted. That's why we have 0 ultimately. What happens when A is closed and B is open? At that time we will have the values A is equal to 1 and B is equal to 0. At this stage also we have the result as 0 because it will not conduct, that electricity flow will be stopped here. What happens when both are going to be open as we see in this diagram? It is going to give you 0 again, stating that no flow is there. So whenever you find the switches in series arrangement, you should understand AND operation is taking place. When we have some arrangement in series, definitely the next arrangement will be parallel. Parallel arrangement will be in this way. You have the voltage source here and you have the lamp here. Now we have two transistors in parallel arrangement. This is actually in open position. Open means A is equal to 0 and B is equal to 0. Whatever electricity flows here, it will stop by here. It will not flow to the other part. So here the result will be 0. What happens when A is closed? That time A turns 1 while B is going to be 0. Electricity may not take this route, but it will flow through this route and then reach the lamp. So that way we can say the result will be equal to 1. What happens when A is equal to 0? That is when it is open and B is going to be closed. At that time B will be 1. At that time what will happen? Electricity will flow through B and it will reach the lamp. That's why here also the output is 1. What happens when both are closed? That is when A is equal to 1 and B is equal to 1. Electricity will flow either way and reach the lamp, and that's why the output is 1 again. Now what is parallel arrangement depicting? It is giving the logical OR operation A or B or A plus B. So 1 plus 0, 0 plus 1, 1 plus 1 will give you 1, while only 0 plus 0 will give you 0. Instead of changing the switch manually, an electronic switching circuit uses binary signals to control the conduction or non-conduction state of the active element. So based on 0 and 1, it will decide whether to close the switch or open the switch. That is what they say by means of using binary signals, which are nothing but zeros and ones here. Now we will continue with the other gate operations that we saw in the right hand side. The first gate that we are going to consider is a NAND gate. What is actually NAND? It is not of AND gate. So this is going to be the AND gate and this is going to be the inverter gate. This is actually the graphical symbol of NAND gate, but how it is working, that elaborate working is given here through the circuit that is present in the bottom half of the screen. So now we will supply inputs and check. Let x is equal to 0. So whenever I supply input to the first diagram, the input will be supplied to the second diagram also to tell you how it is taking place. Y is also equal to 0. Now what happens? What is x into y? 0 into 0 will give you 0. That's why you have a red signal here. What happens when an inverter is used? It becomes green. It means the value turns as 1. From this, we have the value f is equal to naught of x into y as 1. So 0 and 0 will give you 1. This will actually reverse the output of AND gate. What did we get in AND? 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. This is AND truth table. Just check, we will have the reverse of the output now. We will have x is equal to 0. The value of y will be changed to 1. What is 0 into 1? We will have 0 again. And when it is inverted, we will get 1 here. So 0 and 1 will also give you 1. So now you can see the first row has 1, the second row has 1. What about x is equal to 1 and y is equal to 0? 1 and 0 will give you 0 again. When it is inverted, it will give you 1. 1 and 0 will also give you 1, which is the reverse of third row. What about x is equal to 1 and y is equal to 1? 1 into 1 will give you 1 only in AND operation. But when you invert 1, it becomes 0. So 1 and 1, when they are passed into the NAND gate, it will give you the value of 0, which is again the inverted value of AND gate value. This is how the NAND gate will work. This is the overall symbol that you should use. As I said earlier, this is actually the detailed circuit. This particular symbol is actually the inverter symbol. This is the AND gate symbol. That is what is elaborately represented here through this diagram. There is nothing wrong when you use this diagram, but when there is a specific gate for NAND, you have to go with this. Though the output is going to be the same, this is just used for explanation purpose alone. So what is NAND gate? F is equal to 0 only when both x and y are going to have the value of 1. Otherwise, the value of f will be 1. So when either x is 0 or y is 0, or when both x and y are going to be 0, ultimately due to the inverter operation, we are going to get 1 in the first 3 rows. The algebraic function is given by negation of AND operation. So this is AND operation. This has to be performed first. That's why we have given brackets and then used dash. So this can also be mentioned in this way. Next we will move to NOR gate. So from the word NOR you can understand it is not of OR operation. So let's take the OR truth table. 0, 0 will give you 0, 0, 1 will give you 1, 1, 0 will give you 1, 1 and 1 will give you 1. So now the reverse will be 1 0 0 0. Let's check that. Let's take x is equal to 0, y is equal to 0. 0 plus 0 will give you 0 and the inverter part will give you 1. So 0 and 0 will give you 1. Here we have 0 and here we have 1. What about the second row? X is equal to 0, y is equal to 1. 0 plus 1 will give you 1. When you invert 1, you get 0. So 0, 1 under NOR operation will give you 0. X is equal to 1, y is equal to 0. 1 plus 0 will give you 1. Inverting 1, you will get 0. 1 NOR 0 will give 0 as the F value. What about x is equal to 1 and y is equal to 1? 1 plus 1 will give you 1. When you pass it through the inverter gate, this becomes 0. So 1 and 1 will give you 0 here. F is equal to 1 only if both x is equal to 0 and y is equal to 0. F is equal to 0 when either of the value is going to have 1 or when both of the value will be 1. The algebraic function is given by x plus y the whole complement or the whole negation. This is the OR operation and this is the NOT operation. That is what it is mentioned as NOT of x plus y. Next we will move to exclusive OR gate. So the exclusive OR symbol is this one. This is the detailed circuit through which the values are going to pass. So what is actually exclusive OR going to do? X into y negation is found. Then x negation into y will be found. These two values will be sent for OR operation. What is the symbol of XOR? It is this one. Exclusive OR is actually called as XOR. Now we have x is equal to 0. When we have an inverter operation here, x dash, what will be the value here? 0 will invert as 1. So this is the x part. Now let's get into y is equal to 0. So y is supplied to this AND as well as this AND. Now y dash should be inverted. So this will be 1. What is this? It is 0. What is this? It is 1. Again, what is this? It is 1. This is 0. What is 0 and 1? This will give you 0. What about 1 and 0? It will give you 0. What is 0 plus 0? It will give you 0 and that is the output that we get here. So 0 XOR 0 will give you 0. Just remind propositional logic. Whenever you have the same input, you will get false. Whenever you have different inputs, that time you will get true. The same thing is applied here. Now we'll go for x is equal to 0. So here we have x in 2 lines and x dash is given with green line. What about y? Y is equal to 1. So 1 is supplied to this particular AND gate and it is supplied to the inverter gate here. When 1 is inverted, we get 0. Now just find the AND operation of 0 and 0. It will give you 0. 1 and 1 will give you 1. So remember, red signal is for 0, green signal is for 1. What is 0 plus 1? It will give you 1. So when the inputs are different, when x is having 0 and y is having 1, we get the output 1. Now we will get to the third row. X is equal to 1. So what happens to the x dash here? It becomes 0. Now y is equal to 0. What happens to y dash here? It becomes 1. Now we have 1 and 1 in the first AND gate, which will give you 1. We have 0 and 0 in the second AND gate, which will give you 0. What is 1 plus 0? It will give you 1. So ultimately the third row will have 1 under x, 0 under y and 1 under f. Again the inputs are different, so we get a 1. What about x is equal to 1? So we have x dash is equal to 0. Now the value of y is also going to give you 1. What about y dash? It will change to 0. Now it is a combination of 1 and 0 which will give you 0 and 0 and 1 which will again give you 0. What is 0 plus 0? It will give you 0. So when the inputs are same with value 1, we get 0. So there we saw when the proposition P is equal to true, Q is equal to true, we get false. And when the proposition P is equal to false and Q is equal to false, we get a false. Whenever they have different values, we get true. The same logic is applied here. So remember, this is the graphical symbol of XOR gate. F is equal to 1 when either x is equal to 1 or y is equal to 1. So at a time only one of the value can be 1. F is equal to 0 when both x and y have the same value. Whether they are 0 or 1, it doesn't matter. But when they have same value, it ends up with 0. So what is the algebraic function? Though we represent it using XOR symbol here, the algebraic function is x and y dash plus x dash and y. We saw the precedence of logical operation. In that I will just pick up only 3. This is the order. So we will have 1, 2 and 3. This is negation, this is conjunction and this is disjunction. Now just take where is negation? It is in y dash and x dash. So it is computed first. After that you have to go with AND operation. That's why we are computing these two values. So at a stretch we are computing AND here and at a stretch we are computing AND here. These two AND together should be combined under OR operation. That is what we do here. So the negation comes first, the AND comes next and the OR comes next. You have to see the precedence here. It is starting with negation, moving to AND and moving to OR. We didn't use any parenthesis here to mention this should come first or that should come first. Based on this precedence order that we saw in propositional logic, we are applying it here in the context of hardware. Now we will move on to the final gate, exclusive NOR. This gate is also called as equivalence gate. So this is another term that you should remember. Now just see the function. We have two negation operation. One is for x dash and another one for y dash. Then we have two AND operation. X into y, x dash into y dash. Then we have OR operation. So this is NOT, this is and this is OR. So just see, first we are going for NOT, the negation operation. Then we are performing AND as per the precedence. Then we are moving to the OR operation. This is just to give you the flow. What about the graphical symbol? This is how we represent XNOR. Along with the XOR symbol, you are just using the inverter here. So when you took NAND, along with AND symbol, you used inverter. When you took NOR, along with OR symbol, you used inverter. You used a different arc here to represent it is XOR. But when it is XNOR, along with this XOR symbol, you have to negate it here. This is the perfect graphic symbol and as I said earlier, it is the detailed circuit representation. Let's start with x is equal to 0. Now we have to find x dash, so we are converting it to 1. What about y is equal to 0? Now we have to invert y dash. So what is 0 into 0? It will give you 0. What is 1 into 1? It will give you 1. So 0 plus 1 will give you 1. What does XNOR do? It will invert the value of XOR. What did we get in XOR? We had 0, 0, that is 0, 0, 1, then we had 1, we had 1, 0, then we had 1, we had 1 and 1, then we had 0 here. This is XOR gate. Now just check. 0 and 0 will give you 1. What does XNOR do? Whenever we have same input, at that time it will become 1. You can equate this to biconditional statement. When you have the same input, you are ending up with true. When you have different inputs, you are ending up with false. Now let's go with x is equal to 0. Now let's not disturb x dash. We'll go for y is equal to 1. So now y dash will become 0. So you have a combination of 0 and 1, 1 and 0 here. Both the inputs to the OR gate will turn as 0 now. 0 plus 0 will give you 0. So when the inputs are different, you have 0 here. What about x is equal to 1? X dash will become 0. What about y is equal to 0? Y dash will become 1. Now also the AND operation will end up with 0 because it is a combination of 1 and 0 and 0 and 1. So 0 plus 0 will again give you 0. So here also due to different inputs you are getting 0. Just the reverse of XOR output. Now we have x is equal to 1. There is no change in x dash. When y is equal to 1, y dash becomes 0 here. 1 and 1 will give you 1. 0 and 0 will give you 0. Ultimately you will have 1 plus 0 which is equal to 1. So when the inputs are same, we again get 1 here. So what is the symbol of XNOR? It is using this particular symbol. When you have circle around plus, that becomes XOR. When you have a circle around the dot operation, it is XNOR. F is equal to 1 only when both x is equal to 0, y is equal to 0, or x is equal to 1, y is equal to 1. Only when they have the same values, it will end up with 1. F is equal to 0 when either x is equal to 1 or y is equal to 1. At a time, if only one of the input is going to be 1, then f will be 0. So what is the algebraic expression? X into y plus x dash into y dash. So basically you have to negate them, then do AND operation, then combine them with OR operation. This is the order. What are the common operations here? We have NOT, we have AND, we have OR. When you take NAND, when you take NOR, when you take XOR, when you take XNOR, all these 4 gates are depending on negation, conjunction, disjunction, otherwise called as NOT and OR. Though you have a very small symbol to represent it, this particular notation is having the meaning of this particular expression. So how this expression is working is what I wanted to tell you through this detailed circuit representation. This is going to give a sample working problem. Let's get into the first problem. List the truth table for 3 variable exclusive OR gate. So far we have been working with 2 variable input. Now the question is, are only 2 variables allowed here? Not so. You can extend the inputs. So this is one such example with the extension of input. So let's take the XOR operation. So XOR gate will have 0 when the inputs are same and they will have 1 when the inputs are different. In propositional logic video, we would have used true and false arrangement for the values of variables. But here since it is hardware related logic gate content, we are going with the binary signals, zeros and ones. So true is for 1, false is for 0. So whenever you arrange in binary part, you will always start with 0, 0, then go with 0, 1, 1, 0, 1, 1. But when you go mathematically, you will start with true value. So here we have 0, 0, 0, 1, 1, 0, 1, 1 for x is equal to 0. And we have 0, 0, 0, 1, 1, 0, 1, 1 for x is equal to 1. This is how we have got the 8 rows here. So let's first compute for x XOR Y. Here we have same values, so we will have 0 here. Here we have same values, so we will have 0 here. What about the other 4 rows? 0, 1, 0, 1, it will give you 1. 1, 0, 1, 0 will give you 1. Now we have to add another input here, X XOR Y XOR Z. We can take only these two columns. So 0 and 0 will give you 0. 0 with 1 will give you 1. 1 with 0 will give you 1. 1 with 1 will give you 0. Because here we have same set of input. We are going to take it this way. 1 0 will give you 1. Then 1 1 will give you 0. Then 0 0 will give you 0. 0 and 1 will give you 1. Since both the operations are same operation, I did not reverse the column, but in general, first you have to compute these two, then do the XOR with Z. So finally we have got this particular value here. So how do you represent them? When we want to represent XOR, we can represent through 3 input. So this will go this way, and overall you can have X XOR Y XOR Z. This is one way when you represent all the 3 inputs through the XOR gate. There is also another way. At a stage you will consider only 2 inputs here, X and Y. So for this X and Y we will have one XOR gate, and this will be X XOR Y. When you have this particular input line and another input line for Z, this will become another XOR gate, and ultimately you will have X XOR Y XOR Z. Next problem, express the following switching circuit in binary logic notation. During explanation we saw switches in series and switches in parallel. So this is A, this is B. So this is series arrangement. What about parallel arrangement? We had A here and then B here. From this what you can understand is this is parallel, which is actually representing logic OR operation. What is logic OR? This is represented by A plus B. So the output of this particular parallel switch will be A plus B. When you have a switch like A plus B, then another switch like C, what is this arrangement actually? It is series arrangement. What operation does it represent? It is representing logic and operation. This should be taken as a complete term. Along with what variable you are going to do, and along with C. So this will have A plus B into C. Why have I mentioned brackets here? It's because first there is a parallel operation. The result will be A plus B. This result is undergoing a series operation with C. So the output is represented as A plus B into C. So what is the binary logic notation? It is A plus B into C. When you take digital design books, even these kinds of questions are available. So just to give you an idea about the switching circuits, I have just taken this problem. So with this we are completing digital logic gates content. I'll meet you in the next video. Thank you viewers.